Preparation of alkyl halides. See, the alkyl halides can be prepared. Let me put up here the methods of preparation of alkyl halides. The first method is from alcohols. Now, from alcohols we can prepare them by many different ways, like the first one, by reaction with halogen acids. In this, let us see first chlorination. Now, for chlorination we uses HCl and zinc chloride anhydrous. What we do is, the normal system is, when any alcohol is reacted with HCl, the reaction is carried out in presence of anhydrous zinc chloride. What we get is the corresponding alkyl chloride plus water. So the OH group is being substituted by the chlorine and the byproduct is water. The anhydrous zinc chloride is a Lewis acid which is used to make weaker the CO bond in the alcohols, due to which the Cl is easily able to replace the OH. Otherwise, it is not possible. Now, the example of this we can take it as when ethanol is reacted with HCl in presence of anhydrous zinc chloride. What we get is ethyl chloride plus water. Now, this HCl and ZnCl2, the mixture of these two in 1:1 ratio is called Lucas reagent. Now, this mixture is used to distinguish mixture of HCl and ZnCl2 in 1:1 ratio is used to differentiate primary, secondary and tertiary alcohols. How? You can see here, if we have this primary alcohol and suppose this is the secondary isopropyl alcohol we have, and we also have our tertiary alcohol. Now, when all of these are reacted with HCl ZnCl2, HCl ZnCl2, HCl ZnCl2, what happens is, in case of tertiary alcohols, we get the third butyl chloride immediately, which appears as a what? White turbidity, which appears immediately. Whereas in this case, we get isopropyl chloride. This also appears as white turbidity, but this appears after some time. So that's the difference. If in any sample, on adding this Lucas reagent of alcohol, if we get white turbidity immediately, it's a tertiary alcohol. If we are getting white turbidity after some time, it is secondary alcohol. And even and if we are not getting any reaction done, no turbidity, it means it's a primary alcohol. This only shows on heating, that when we heat this left out one which is not showing any turbidity, then only the reaction takes place in such a case and we get the corresponding alkyl chloride plus water. So this is how the primary, secondary and tertiary alcohols can be distinguished from one another, and this also shows that the reactivity of the alcohols is in the order that tertiaries are most reactive, followed by secondary and then primary. What makes them tertiary most reactive is the formation of the tertiary carbocation in the mechanism. That is why this becomes very much reactive. Now, if suppose we wanted to introduce B-bromine in place of the alcohol, so what we call it bromination. Now, for bromination, the reaction is with HBr is used with sulfuric acid, which is found to be 48%. 48% sulfuric acid is taken. Now, the scheme of the reaction is very simple. That when alcohol is reacted with HBr, the OH group is being substituted by the Br, and this is how we get alkyl bromide, and what we do is we get water. Now, this reaction is done by continuously heating the reaction mixture in the flask, which we call it reflux, for 4 to 5 hours. Now, this reflux is mainly used when we have a primary alcohol, but in case of tertiary we don't need any reflux. So, if we have a tertiary alcohol which is reacted with HBr in presence of sulfuric acid, what we get is tert butyl bromide along with water, and there is no need of any reflux. Whereas in the same case, if we have a primary alcohol, yes, we have to take HBr, H2SO4, and we have to take reflux, and then only we get the corresponding bromide. Whereas for iodination, what we can do in case of iodination is, for iodination, Hi is used with phosphoric acid, H3PO4, almost 90% pure, and the scheme of the reaction is very simple. When any alcohol is reacted with Hi in presence of H3PO4, iodine replaces the OH group, we get what? Corresponding alkyl iodide plus water. This is what we get. Now, if suppose we have a primary alcohol, we need to take Hi, H3PO4, and reflux is also done, continuous heating, then only what we get is corresponding alkyl iodide and then water. But if the alcohol is tertiary, what we find is there is no need. The Hi, being the strongest halogen acid, directly reacts to form the corresponding tert butyl iodide plus water. So, this is how the reactions we can do what we can replace the OH group by the halogen, and the reaction is done with HX. The second method of obtaining alkyl halides from alcohols is by reaction with PCl5, PCl3, PBr3, Pi3, or thionyl chloride SOCl2. See, all these PCl5, PCl3 and SOCl2, they are called chlorinating agents. They easily replaces the OH group. So, if we have any alcohol and we have PCl5, and we react it, we get corresponding alkyl chloride along with phosphorus oxychloride and HCl. Whereas if we have any alcohol, whether it is primary, secondary or tertiary, whatever it is, PCl3 gives along with this alkyl halide phosphorus acid, alkyl chloride phosphorus acid. Whereas what we have is when it is reacted with this thionyl chloride, what we get is alkyl chloride plus SO2 plus HCl. Now out of these three, remember this R can be your primary, secondary or tertiary group, it can be any one of these. And what we find is that out of these three methods, all these three are called chlorinating agents because they easily replaces the OH by the Cl. What we find is this method is one of the best one because both the byproducts are gaseous in nature, so they leave the pure alkyl chloride left out in the reaction mixture. Whereas, yes, we can use any of the PCl5 or PCl3. This we have also seen in the P block where we have done the properties of PCl5 and PCl3. Now, along with this, what we can do is we can use these PBr3 or Pi3. This is done for bromination. This is used for iodination. What we find is that they are prepared always in situ. Why? Because PBr3 and Pi3 are not stable. So what we do is we always take red phosphorus plus bromine, which gives us PBr3. When the same red phosphorus is taken with iodine, what we get is Pi3. So they are always prepared in situ, and what we find is if we take any alcohol and we treat it with PBr3, what we get is corresponding alkyl bromide and phosphorus acid. And if we take any alcohol and we treat it with phosphorus iodide, Pi3, what we get is corresponding alkyl iodide plus phosphorus acid. So in this case also R can be your primary, secondary or tertiary, any of these alcohols. Now the second method of preparing the alkyl halides is from hydrocarbons. Now from hydrocarbons, let us take first from alkanes. When we take from alkanes, the reaction is done by free radical substitution reaction, substitution mechanism. Now what we do in this case is, if we have like this propane with us, this on chlorination in presence of UV light gives us what? All sort of substituted products, like we get isopropyl chloride as well as N-propyl chloride. Though we know that this will be the major product, this will be the minor product. The reason is because both alpha as well as beta hydrogens are being substituted by chlorine by the free radical mechanism, and since beta is giving us a more stable alkyl halide, definitely beta 1 is formed, the isopropyl is formed in a major quantity. But what we get is, yes, always the free radical substitution reaction of the alkanes gives us a complex mixture of the one or polyhalogen compounds, and which are very difficult to be separated. That is why this method is not very suitable for the preparation of a particular alkyl halide. That is what we never prefer it. But yes, it can be used. And in this place, like suppose we use the same one, we use as bromine. Yes, bromination can also be done by using the same method. What we get is, yes, same alkyl isopropyl bromide, and we can also get what? N-propyl bromide. We can also prepare alkyl halides, yes, from hydrocarbons by taking alkenes. Now this reaction follows an electrophilic addition reaction. And the simplest way is, like if we have this propene with us, we are using bromine in CCl4 nonpolar medium. What we get is bromine is added across the double bond. So we get what? Vicinal dihalide or vicinal dibromide. In this case, Similarly, chlorines can also be added. Whereas if we are adding the addition of HX is done in this propene like HCl is done, we know Markovnikov's rule is followed, which states that during the addition of a heteroatomic species to unsymmetrical alkenes or alkynes, the negative part goes to the more substituted carbon. So the Cl minus of this will go to this secondary carbon, which is bonded to the two other carbon atoms. Because what happens is this reaction follows the stability of a carbocation. Secondary carbocation is formed on which the nucleophile attacks, but first the electrophilic addition takes place, due to which a more stable carbocation is to be formed. So what we find is CH3, CHCl, CH3, this product is formed. This is what is called Markovnikov's rule. Here we also know one very basic thing, that if we are adding suppose we are having like in this case, in this propene, we are having HBr, yes, Markovnikov's rule is followed. What happens is Br will go to the central carbon, we get isopropyl bromide. But simultaneously we know, we have done in class 11th, that if this compound is, on this compound HBr is added in presence of peroxide, in place of electrophilic addition reaction, free radical addition takes place, and the reaction follows what? I will just add a word anti before. It follows anti-Markovnikov's rule, which is also called peroxide effect or Kharash effect, in which what we find is CH3, CH2, CH2, Br is formed. The bromine goes to lesser substituted carbon. The reason is more stable free radical is formed, and the bromine goes to the carbon which is less substituted. They're exactly opposite to this one. But we also know that this anti-Markovnikov rule is only applicable to HBr. It is not applicable to HCl because bond enthalpy is very high. Because of this doesn't happen. Whereas in case of HI, yes happens, but iodide radical is not stable. So we are only left with HF also is having very high bond enthalpy. That is why in both these cases what we find is because of bond enthalpy that doesn't take place. HI, iodide radical is not stable, so that doesn't show this anti-Markovnikov's rule, so we are only left with HBr. So anti-Markovnikov rule is only applicable when HBr is taken along with peroxide. Even if we are taking HCl in presence of peroxide, this reaction doesn't take place. So this is how we can add, yes, alkyl halides, or we can prepare alkyl halides from the alkenes by the addition of either the halogen acids or directly the halogens, which shows electrophilic addition reactions. Let us see the preparation of the aryl halides from the hydrocarbons. So the third method is that we can prepare by electrophilic substitution reactions on aromatic hydrocarbons. Like suppose we have this benzene, we can put bromine here, Fe, dark. What we find is we get bromine here and HBr. So this is how we can prepare bromobenzene. So I can write out very simple reaction, X2, and we can write Fe. What we get is X. Here X can be chlorine, bromine, or iodine with HI. In case of HX, if we are taking iodide, remember the reaction is carried out in presence of the oxidizing agents like iodic acid or nitric acid. Because HX, the HI form, makes the reaction reversible. These oxidizing agents consume the HI form and doesn't let the reaction to go in the reversible direction. That is how, if we want to prepare aryl iodides, we have to prevent HI from reacting again with the aryl iodide formed, so that the reaction doesn't become reversible. We can also take another example, that if we are having, suppose in this place, in place of this toluene, we know toluene, in this toluene the methyl group shows plus I effect, and due to hyperconjugation it is ortho and para directing. So when any of the halogen is treated with this in presence of dark, we are taking dark because if we are taking it in light, what happens is free radical substitution of the benzylic hydrogens takes place. So what we get is, we get ortho and para products, in this case CH3X, so ortho product, and we also get para product, and major is the para product, HX is the 1pi product formed. And always again in case of iodine, the HI is to be removed from the reaction mixture so that the reversibility of the reaction is avoided. So this is how we can easily prepare, and para will always be the major product because of the symmetry. We can also prepare aryl halides by Sandwell's reaction. It's a name reaction. In Sandwell reaction, what we do is we convert first aniline to BDC, this is called benzene diazonium chloride, BDC. How this is done? By reacting it with NaNO2 HCl at 0 to 5 degree ice cold conditions. So the nitrous acid form converts the aniline into BDC, benzene diazonium chloride, on which, due to this positive charge on the diazonium group of the nitrogen, very easily what happens is nucleophilic substitutions can be done. That is why when this BDC is treated with cuprous chloride, suppose let me write it like this. If we treat this with cuprous chloride, what we get is chlorobenzene, and when it is treated with cuprous bromide, what we get is bromobenzene. So these are the two products formed along with what? HCl and nitrogen, along with HCl and nitrogen, and these are the best ways, one of the best ways of preparing what these aryl chlorides and aryl bromides. Along with this, we can also prepare aryl iodide. Yes, the same BDC on treatment with Ki easily gives us what? The aryl iodide, and along with this, of course, nitrogen and HCl. So this is how we can prepare aryl chlorides, bromides and iodides. By what? Through BDC we can easily be prepared. The next method of preparing the alkyl halide is by halogen exchange. And the most common example of this category is Philkinston reaction. See, we know that we can't prepare alkyl iodides directly, or if we are preparing it, the yield is poor. So the alkyl iodides mainly are prepared by this Philkinston reaction, which is also called halogen exchange method. Now in this, what we do is the alkyl chlorides or bromides are treated or reacted with sodium iodide in presence of acetone. So iodide, being a stronger nucleophile, replaces chloride and bromide, and what we get is alkyl iodide and sodium chloride or bromide. So this is how the iodides can easily be prepared from the already prepared alkyl chlorides or bromides by simple halogen exchange. Now this reaction is, the reversibility of this reaction is not possible because chloride and bromide are not strong enough as a nucleophile to replace iodide ion. So that's why this reaction easily forms alkyl iodide. There is another method of preparing the alkyl by halogen exchange, which is mainly used for alkyl fluorides. Now that reaction is called Schwarz reaction. Now in this Schwarz reaction, again alkyl chlorides or bromides are heated with metal fluorides like silver fluoride or cobalt fluoride or arsenic fluoride, like mercury fluoride. So they all are, any one of these can be used. So they are heated when the alkyl chlorides or bromides are heated with these metal fluorides. What happens is fluoride easily replaces this halogen chlorides or bromides and form alkyl fluoride, and the AgX correspondingly comes out. So this is again is a very simple reaction in which the metal fluorides easily replaces the fluoride from the metal fluorides, easily replaces the chlorides and the bromides, and what we get is corresponding alkyl fluoride.